Okay, so today we will start a new chapter, chapter 8, root systems. So in the last chapter, we learned that when we have a semi-simple Lie algebra, G, then we can associate, we have like a root, and the set of roots is called the root system of G. And we show that this root system must satisfy several properties. And what we are going to do in this chapter is that we will just define root systems just by imposing these axioms. So we can forget about the semi-simple Lie algebra. We can just define this just abstractly, and then we will study their properties. Okay? But of course, these properties will be used later to really understand semi-simple Lie algebra. So we will later use these results in this chapter to construct irreducible representations of a semi-simple Lie algebra. And most properties here in this chapter can be proved using elementary linear algebra. So we have due to time limitation, I have to omit many of them, most of them, unfortunately. But they can be proved just by using basic linear algebra, and they are very well explained in the textbook. So if you're interested, you should read the proof in the textbook. So instead of giving you the details of the proofs, I will try to give you the idea behind these theorems or propositions using examples. So first section is about abstract root system. So the definition. We've already seen this, but yeah, we need to state this again because now we know nothing about semi-simple Lie algebra. So a root system is just a pair denoted E, R, where E is, say, where E is a finite dimensional real vector space with, so it's like Rn, R to the n, with inner product like that. And what is this R? This is just a finite collection of non-zero elements. In E. So it's just a finite subset without zero vector, such that satisfying the following four conditions. First, E is spanned by the elements in R, and these will be called roots, of course. And second, but doesn't mean that it is, they are linearly dependent. They are actually not. They're always not always linearly dependent. If alpha is an element in R, then C alpha is in R for a constant multiple, if and only if C is plus or minus 1. So we've already seen things like this. And if we have two elements in R, then S alpha dot beta is also an element in R. Here, of course, this is the operation, which is the reflection about the hyperplane orthogonal to alpha, right? So in the explicit formula, it can be written in this way. So it's a reflection about a hyperplane. And finally, for all alpha, beta in R, 2 beta over alpha comma alpha is always an integer. So for every semi-simple Lie algebra, the associated root system satisfies these four conditions. So now we just define a root system to be a collection of vectors satisfying these conditions. Okay? So very simple, just four axioms, but there are many, many interesting properties of root systems. We will see them. And we say that the rank of the root system, say ER, is defined to be the dimension of the vector space E. So real dimension of the real vector space, of course. And the elements of R are called roots. So root system is the root system is basically a collection of roots. Okay. And maybe I can recall here. So the meaning of 4 means the condition, the final condition for this means when we have two vectors, say beta and alpha, like that, then we can consider the orthogonal projection here, right? This is orthogonal projection. We can write C alpha because it's parallel to alpha. Then that means this is orthogonal projection. Then this means the orthogonal projection of alpha beta onto alpha is what? A half integer, or like this, half of alpha integer, or integer multiple of alpha, like that. So in this case, let's say this is half of alpha, then it is fine. Okay? And of course, if we project alpha onto beta, in this case, this is projection of alpha, and it's just beta, so it's a constant or integer multiple of beta, so this is okay. Basically, these four last condition says this thing, geometric meaning of that. Yeah, sometimes people consider root systems without some of these conditions. For instance, sometimes people just consider root system without the last condition, and it's called non-crystallographic root system. So when we include 4, then usually it means crystallographic, and sometimes people don't consider 2 and then say that if without 2 is usually called non-reduced, and if there is 2, it's reduced. But it's just some kind of technical condition, technical terminologies. But in this chapter, we will always consider root systems with all of this. But maybe if you go to some talk in combinatorics or algebra, you may hear that crystallographic root system, but if you hear that, that means 4 is included. But usually, in this semester, we only consider this. That means we only consider reduced crystallographic root system. Okay? But these are just some technical terminologies, so you can forget about them if you are not interested in this. So we always have these 4 conditions. Okay. And another note. So they came from this root system. They came from semi-simple Lie algebra. So the root system of semi-simple Lie algebra is okay. every root system of a semi-simple Lie algebra satisfies these conditions, right? So that means root system of a semi-simple Lie algebra is really a root system in our definition, right? Or abstract root system. And conversely, any, say, abstract root system. So abstract root system is the root system I defined, okay? Abstract root system arises in this way. Meaning that whenever we have a root system, in fact, we can find a semi-simple Lie algebra G whose root system is the root system we started with, okay? So in fact, they are really the same. Okay, so we can define many objects associated to a root system. Okay, so ER, say, is a root system. Then the while group denoted W as before of R is the subgroup of the orthogonal group on this vector space E, right? The group of all orthogonal transformations generated by these reflections S alpha in the root system. Okay? So this is, yeah, it's the same as before. Like when we had this semi-simple Lie algebra, we had root system, and the while group can be defined this way. So it's the same thing. Okay, and recall that by the condition here, by the condition of which one? Third condition means that while group permutes the roots. When you have a root, if you apply a while group element, it cannot go outside of this R, right? It has to be inside. It has to be a root. Whenever we have a root, say beta, if you apply, this is a while group element, right? If you apply a while group element to beta, it's still in alpha. It's still in the root system. That means a while group acts on the root system. So the root system, okay, so W acts on, okay, let me write this way. W is a finite group, finite subgroup of, it's not just any subgroup, but it has to be a finite subgroup permuting the roots. Because it must send one root to another root, and because we know that the root spans the whole space, if you know which root sends to another root, then we know exactly what this group does. So it is a permutation. In fact, it lives inside the permutation group of the roots, which is finite. So W can be considered as a subgroup of the symmetric group of R. That means permutation group, if you want. The same thing. So if there are n elements in the root system, then the permutation group, in the permutation group there are n factorial permutations, right? So in W is a subgroup of that. It may contain all of them, but usually not. And so another note is that W after all, W is subgroup of O of E. That means it's a orthogonal transformation. So W acts on E, right? By just the WH like that. When W is in W, H is in the vector space. This is just a usual transformation applied to a vector, right? Or maybe I should write something like that. They're the same thing. And W also acts on R, like that. So W is in fact acting on R. Okay. All right. And we will, when we have root systems, as a usual, kind of a usual step in when we study mathematical object the first time. When we define something, and then by combining these, we want to make a bigger one, right? It's like this proposition 8.3. Suppose that we have two root systems, ER, FS. So it's a root system. So EF, they are real vector spaces, R as root systems or set of roots. And we define, we can define E direct sum F. You can always take the direct sum of two vector spaces, and we take the union of R and S. This is a root system. We can make a bigger one. And this is called the direct sum of R and S. So direct sum. Of course, we have to define exactly what this means. So here, okay, we have to say something, because when we have a root system, this is a real vector space, but we also have an inner product. We must specify an inner product here. We have an inner product here, but what is the inner product for this? So here, the inner product on E direct sum F is the natural one. Say induced from the inner product in E and the inner product in F. What does that mean? So that means, so element here is a pair of element in E, element in F. So suppose that we have an element here, E prime, F prime. So how can you define the inner product? That the natural one is E prime plus F prime. Just component-wise, we do this. And of course, we have to say a little more precisely what these are, what the elements here. Because technically, this is not, R is in E, S is in F. So technically, this is not, they are not really an element in this. But of course, there's a natural way to embed them inside this. So, and R is an element, a subset in E, but this naturally lives in F by the identification E comma 0. Thus, we have 0 component for this F. And of course, S also lives inside this direct sum by the, like that. But then, note that in this inner product with this direct sum, E and F, these two spaces, they are orthogonal with each other. So E and F, these two are orthogonal spaces. Because, so element here is represented by E comma 0. Element here is 0 comma F. So what is the inner product? This is like E comma 0 in E, 0 comma F in F, but of course 0 plus 0 is 0. So whenever you take a vector in E, vector in F, in this Dirac sum, their inner product is 0, meaning that E and F, they are orthogonal complement. So orthogonal Dirac sum. Okay. So for example, let's take a very simple example. Both E and R is just a one-dimensional with A1, type A1 root system. That is this, right? We have only two vectors, alpha and minus alpha, in just one-dimensional space. And let's say F and S, just the same thing. So we have another stuff like that. Then what is the inner product? What is E inner product F, R, S, the Dirac sum of, let's write over here, it is something like that. We take so this is E, and this is F. We take the orthogonal complement, or orthogonal Dirac sum of them, and then the vector is just, we just take the union of the roots. So this is, usually it's denoted by A1 times A1. So Dirac sum, so usually it's denoted like R times S. But as you can imagine, when we have two root systems, and then if you take the Dirac sum, and then what's going on here is really just they kind of do not interact at all. So if you can understand one part and the other part separately, then you can understand the Dirac sum. So we will be mostly interested in a root system that cannot be decomposed like this. Because if it can be decomposed like this, we can just look at the component, orthogonal component separately. So we need to have a definition for that. So definition, a root system. So ER is a root system. This is reducible if there exists an orthogonal decomposition so decomposition like E equals E1 Dirac sum E2 such that of course it must be non-trivial, dimension of E1, dimension of E2, they must be non-trivial vector space. And for all roots, for every root in R, we have either alpha is in E1 or alpha is in E2. It must be in alpha exactly in one part, not the combination of them, right? That means, basically it means that we have a decomposition of the root system. Otherwise, if such a decomposition, orthogonal decomposition exists, then we say that this root system is reducible. Otherwise, E comma R is called irreducible. So, in fact, let's say, suppose that E comma R is an reducible. With this decomposition, satisfying these conditions, then let R1 be the intersection of R in E with E1, R2, R intersect E2. Then of course, then by the assumption here, R is the union of R1, R2, right? Because everything must be in one part, not a combination of them. So for instance, if E1 is this is E1, this is E2, then the root must be something like this, like A1. We cannot have a root like this, right? That's what this condition is saying. We always have roots like that, like A1 cross A1. In this case, E1, R1, these two, one can check. These are root systems. And of course, and this is a direct sum of these two root systems, R1 and R2, right? So reducible means we can write this as a direct sum of two non-trivial root systems. All right? All right. And in fact, in the last chapter, we have seen something like this. So let's record that. So thus, a root system is reducible. That is if and only if it is a direct sum of ER is a direct sum of two root system, non-trivial root system. And recall that root system the root system of a semi-simple Lie algebra say G is reducible if and only if G is simple. This is a fact that's very useful for the study of the semi-simple Lie algebra. That means if you know the root system, you can tell whether the semi-simple Lie algebra is simple or not. It's a very powerful theorem. Okay. And the next thing you can imagine, we have two root systems. Sometimes they have different names, but they are basically the same. So we want to say that two root systems are the same or not. So using isomorphism. So two root systems, these are isomorphic if there exists an invertible linear transformation, say A from E, the real vector space E, to the real vector space F, such that it sends a root in one side to the root in the other side. So we expect to have this property. And moreover, and for all alpha, beta, A of S alpha beta equals S A alpha A beta. And such a map A is called an isomorphism, as usual. So, what's the meaning of this? Okay, this one is, we must have this invertible linear transformation, means it's isomorphism between vector spaces, right? That's something we must have, for sure. And yeah, we expect to have, we want to send one root here, all the roots here to the old roots there, right? And moreover, this is the condition that we will consider a little bit. So we have a root, and we have this kind of while group element, right? And this can be translated exactly like that. So, but notice that it only kind of preserves the while group structure. But so it sends this reflection, orthogonal reflection, to this reflection. So everything just change it by the alpha. So think of this as vectors in one vector space. We kind of rename them using this isomorphism. But one thing that you need to notice here is that this is not A does not have to preserve the inner product. The inner product may not be preserved. So if an inner product is preserved, that means it preserves the length, right? But it may not preserve the length. For instance, if you have, for example, if you have, let's say, A1, a very simple root system, right? So let's say this is length 1. And then let's say root system of the same thing, but this is 2, length 2 and 2. They are isomorphic. Sending with this A of, say, alpha equals 2 alpha, this is a completely fine isomorphism between these two root systems. Because, when we draw this root as a diagram, we don't really care about the length. I mean, of course, we care for this relative length between two roots, but the absolute length of each root is not really important in our point of view. So if we can obtain from one root system from the other by kind of doing dilation, that gives us an isomorphism. Another less trivial or more interesting example is this. R2 and B2, which is like, let's say, the root system of type B2 is like this. This is B2. And the length here is 1. This is square root of 2, like that. This was the root type B2 root system. And let's say F comma S is the same vector space, but C2. But C2, we have 1, 1, oh, not 1, 1. We have 2, 2, 2, 2, and like this. So the length here is 2, length here is square root of 2. But they are isomorphic. They are isomorphic. What is an isomorphism? Isomorphism, like a rotation by the angle of 45 degrees, and dilation by a factor of, say, 2, no, square root of 2. If you rotate this 45 degrees, and then if you make every vector dilated by a factor of square root of 2, then this becomes 2, this becomes square root of 2, so it gives us an isomorphism between these two. Okay? So basically, you can think of isomorphic, two isomorphic root systems to be exactly the same shape, without, but up to constant multiplication. All right. So in particular, type B2 root system is isomorphic to type B C2 root system, but it's only for n equals 2 case, doesn't continue to hold for general n. Okay, so next. Oh yeah, here's an interesting, simple but very useful proposition. Alpha, beta, they are roots. Suppose that alpha is not a constant multiple of beta, because that case is just trivial. And we may assume that alpha has longer length than beta. Okay, suppose this, then exactly one of the following holds. Here, let's say theta is the angle between, or let me just draw this diagram. Suppose that theta is like this. Theta is the angle between alpha beta, okay? One of the following condition or following holds. First, alpha beta is orthogonal. They are orthogonal. Or they are not orthogonal and they have the same length, like I think it should be alpha. They have the same length, and the angle between them is either pi over 3 or 2 pi over 3. Okay? And third, alpha in the product alpha is 2 times beta in the product beta, and theta is pi over 4 or 3 pi over 4. Or alpha alpha 3 times beta beta, theta equals pi over 6 or 5 pi over 6. We must have exactly one of these 4 conditions. Of course, we cannot have 2 at the same time. So they are exclusive. Okay, so what is the meaning of this? So let's say before proving this, I'm going to prove this, but before proving this, let's let m1 equals 2 times alpha beta over alpha alpha, and m2 be this 2 times alpha beta over beta beta. Okay? So what is that? So in the first case, or the first case is simple. In the second case, we have the same length, alpha for alpha and beta. Let's draw a little more carefully. So this is alpha and beta. And the angle between them is, let's consider only the acute angles, because this case is similar. Here is pi over 3, like a 60 degree. And project this onto here, and basically, what is the factor here? This is like m1. Oh, this is beta over 2, right? This is beta over 2, or maybe I should use this color, beta over 2, and if you project like this, is alpha over 2. Or we have pi over 4. In this case, this is alpha, beta. Project here, this is just the same, beta. If you project onto alpha, this is alpha over 2. The third case, or fourth case, we have something like this. It's 2. So it's pi over 6. This is beta, alpha. And if you project beta onto alpha, it's not very accurate. So this part is 3 beta over 2, or let's write 3 over 2 beta. And this part is still alpha over 2. So in each case, M1 and M2 is always 1, 1, 1. This is 1, 2, 3. Okay? Because M1 is the factor of this constant multiplied to alpha times 2. So here the constant is 1 over 2, so we multiply 2 is 1, always 1, 1, 1. In this case, we multiply 2 to this constant, so it's 1, 2, 3, like that. So we always have this situation for theta, an acute angle. Okay, how can we prove this? The proof is quite elementary. Let's give a proof of this. So what is M1 and M2? Let's multiply them. Just multiply these two. It's going to be 4 times alpha beta squared and alpha beta beta. But we know that this is, this is basically cosine theta. So it's 4 times cosine squared theta, using the usual cosine law, right? And, oh yeah. Of course, let's ignore first case. First case is done. Okay, suppose that first case is no, not the case. Because first case, if it is first case, yeah, that is the first case. Otherwise, now we consider the remaining cases. Okay, so suppose alpha beta is non-zero, not the first case. So because alpha beta product is non-zero, that means they are not orthogonal, right? We can divide this by this. M1 and M2, or M2 over M1. We can divide them like this. This is what? This is just alpha beta beta, which is in particular positive. So M1, M2, their product is always positive, okay? Which can also be seen here. And so M1, M2, this is greater than or equal to 0, and less than or equal to 4, because this is at most 4. Cosine theta is at most 1. So we have, and we know that this is always integer, because that's one of the axioms of the root system. So we have 2 integers multiplied, and then this between 0 and 4. So you know what to do. Just divide the cases 0, 1, 2, 3, 4. Okay. So if M1, M2 equals 0, what does that mean? That means cosine theta equals 0. Cosine theta equals 0 means okay, yeah, actually we don't have to consider it. It's 0, so case 1. If M1, M2 equals 1, or let's say consider 4 first, then cosine theta equals 1. And what does that mean? Then the angle between them is like a 0 or pi. So in this case, alpha must be a constant multiple of this. Is a contradiction. Or it doesn't happen. So we only need to consider the 3 remaining cases, 1, 2, 3. So if M1, M2 equals 1, then cosine theta equals 1 over 4, right? Because of this. And cosine theta equals 1 over 4, that means the angle must be pi over 3 or 2 pi over 3. Okay? Just and these two are integers, and their multiple is 1. That means m1 and m2, this pair must be either 1, 1 or minus 1, minus 1. We don't have any other choices. But in this case, what does that mean? m1, m2, this is positive. That means this is in fact positive. Their inner product alpha between alpha and beta is positive. That means their angle is an acute angle. So in this case, theta is this, pi over 3. In this case, theta is 2 pi over 3. So anyway, this corresponds to case 2. And of course, you know what to do for the remaining cases. If this is 2, then it just corresponds to case 3. And if m equals 3, this corresponds to the case 4. And that's basically the end of the proof. So using the fact that m1 and m2 both are integers, make this very simple. All right. And we will consider one corollary, simple corollary of this. Simple was also very useful. Corollary 8.7, alpha, beta, their roots. And again, this is the angle between alpha, beta. Of course, our root system is given. We are considering two roots of them. If pi over if theta is strictly between pi and 2 pi, pi over 2 and pi as an obtuse angle, then alpha plus beta must be is a root. And if theta is between 0 and pi over 2, so acute angle, then alpha minus beta and beta minus alpha both are roots. Okay. Proof is quite simple. Because we know this previous proposition. All we need to do is consider the cases 1, 2, 3, 4. But the first case we don't have to consider the first because theta is strictly between these or these. So consider each case of these 2, 3, and 4 in the previous proposition, right? So let's consider, for example, I will consider only one case, case 2. Case 2 with, say, acute angle. Let's consider this. Case 2 with this, what is that? Case 2 with theta less than pi over 2, theta must be this. Okay? So let's see. That means theta is pi over 3. So in this case, we just draw this. Let me draw, let's say this is beta. I'm not sure this is very accurate, but you know, it's a little smaller than actual theta, but you know the point. So this is going to be alpha over 2, right? Okay. So what I'm going to do is this. So this is the hyperplane. So this is the hyperplane orthogonal to alpha. Okay. So S alpha will reflect along this hyperplane. Okay. So what is S alpha applied to beta? It's going to be this. So S alpha applied to beta, right? And S alpha applied to beta is equal to, by definition, this is 2 times alpha, beta, alpha, alpha, alpha. What is that? But in this case, case 2, this must be, the whole thing here is 1. So it is beta minus alpha. But of course, this is in the root system by the axiom. And similarly, we can prove the other case. So other cases are similar, so just case by case analysis. And let's see some examples in rank 2, R2 case. So section 7.8.2, examples in rank 2. So because in this case, we can easily draw all the possible root systems. Of course, we have to start with rank 1, but this is almost trivial. We only have this. Alpha and minus alpha is, we have already seen this. So A1, type A1 root system. We have one-dimensional real vector space or real line. We have 2 vectors opposite to each other. So root system. So fine. So rank 2 root system. So there is only one rank 1 root system up to isomorphism. But for rank 2, there are 4 of them. And first is, we've already seen this, alpha 1, A1, A2. With this pi over 2 angle between them. So it's A1 times A1. But notice that their length, they are arbitrary. So here, the length can be arbitrary. The length, of course, these two must have the same length, but for this and this, their length can be anything. And A2 is like this. So all roots, same length. So it's A2. Okay, let's say this theta equals pi over 2. This theta is pi over 3. The angle, smallest angle between 2 roots. And I already drew this. Actually, I think I drew this and said that it's a type C n, but it's really the same as type Bn, so I'm going to say B2 or C2 if you want. Theta equals pi over 4. And the length of the long root is equal to the length of the short root. There are 2 lengths only. Times a square root of 2. So this is 1. If this is 1, then this is square root of 2. So these 4 they are short roots. They have length 1, say, and the long roots, that is a square root of 2 of the length of short root. This one is more complicated, but not that much. Let's try to draw this. Okay. And then so kind of 2 copies of A2 with different length. So theta equals pi over 6, and this is denoted by G2, root system type G2. and the length of the long root is equal to the length of the short root times square root of 3. Because the proposition that we saw tells us that the ratio between the length two roots is always 1 or square root of 2 or square root of 3. Because in the proposition we use the inner product, so its length is the square of them. So yeah. The length, it's possible that we have two different roots, but there are only at most two possible lengths. So we always have short roots and long roots. They may coincide like type A2 and type A2 case. They all have the same equal length, but there are two different lengths, but the ratio is fixed, like a square root of 2 or square root of 3, like that. And the proposition is that these are all possible root systems in type in rank 2. A1, okay, let's just say these are all root system of rank 2, of course up to isomorphism. And moreover, this A1, this is a root system of SO4 and SO4C, which decomposes into SL2, two copies of SL2. And that's why it is, the root system is not irreducible, right? We decompose these into two, so it's like that. And this one we cannot decompose, so it corresponds to a simple Lie algebra, and this case is SL3. Now we've seen something like this, right? And this corresponds to SO5. And this corresponds to something that we haven't seen. So it's called unexceptional Lie algebra. So we've seen these classical Lie algebras like type A, B, C, D. So these four types, they are called classical, but other than these are called exceptional root system. We will look at them later in more details. Okay. So yeah, it will be very useful to consider them as examples of the propositions and theorem that we will see in this chapter. So proposition 8.9. What is that? So say that R is a rank 2 root system. Sometimes we will omit the E, the ambient vector space. Once we know this collection of roots, we know that the E should be the span of this. So it's enough to say that R is a root system. And say that with minimum angle theta equals 2 pi over n. But we know that n must be either one of these, 4, 6, 8, or 12. This is the first proposition that we saw today. Then the while group of R is the symmetry group, not the symmetric group. They mean different thing, of a regular n over 2 gon. This is also called dihedral group of, in this case, of order n, usually denoted dn, like a dn usually. But let's not write that down because dn is kind of type dn, a little confusing. So anyway, it's commonly called a dihedral group. So instead of proving this, I'm going to show you an example. So A2, we have this like that, right? So this angle theta is 2 pi over 6, right? Or pi over 3 if you want. So n equals 3, n equals 6. So the y group is the symmetry group of n over 2, the triangle, of a triangle, regular triangle. So not a symmetry group of the hexagon, but a triangle, okay? So what is a triangle? Actually, we can specify such a triangle. This, so W fixes the blue triangle. Can you see that? So W is generated by reflections, right? So for instance, let's consider this alpha. What is S alpha? S alpha is the reflection about the hyperplane orthogonal to alpha. So it's a reflection about this hyperplane, right? S alpha is a reflection about this. So if you reflect the blue triangle, it stays the same. It's still the same triangle. And if you reflect about, say, this is beta, then what is this is S beta reflects about this hyperplane, and again this stays the same. So you can check everything for every reflection, it just stays there. And in fact, the y group is the same, really the same as the all symmetry group, the group of all symmetries of this triangle. So what do I mean by symmetry group is the following. So you consider all orthogonal groups that, so it's kind of a rotation or a reflection such that it leaves the triangle the same. It may move one dot, one point in the triangle to another one, but as the image must be the same, like this. This one, if you reflect about this, is still the same. Okay, it's like that. So in fact, in this case, W is a dihedral group. It has how many elements? 6 elements, right? So rho, identity, rho, and rho, so where this means rotation by 120 degree, right? Rotation like that. And reflection about S alpha, S beta. Okay, let's write one more, gamma, then S gamma. So these are all elements there. And notice that, note W is not the full symmetry group of R. It cannot, of course, it is a symmetry group of R, but it's a subset of the full symmetry group because, for instance, we cannot get 60-degree rotation. So 60-degree rotation is not in, it is in R, but not in W, right? If you rotate 60 degree, the root system, the roots, six roots are still the same, but it is not in this file group. Okay. to the next section. So duality. Again, we have root system, ER, root system. And for alpha, or root, the co-root is denoted by H sub alpha. This is 2 alpha over alpha comma alpha. This is familiar, right? We've seen this when we study semi-simple Lie algebra. And the dual, the definition co-root, the dual root system denoted R check of R is, of course, the set of all co-roots. You just collect all the co-roots. And notice that for all alpha, beta, alpha and if you take the inner product between alpha and the co-root, it's always an integer. This is exactly the crystallographic condition, or the fourth condition of the root, the axiom, in the axiom of the root system. And proposition, it is really a root system. So dual root system is a root system. So our check is indeed a root system in its own. And our check, the dual of the dual is, as we can expect, itself. Moreover, the while group of our check is the same as the while group of R. So if you take the dual root system, you may get some different root system, non-isomorphic to the original one, but the root, the while group will be the same always. I think we need to see an example, right? Maybe the next page. So let's consider the root system R2 and B2 and C2. So this is B2, so R equals B2. And our check is in this case C2. It's like okay, why is that? Let's say this is alpha and this is beta. The length here says 1 and this length is square root of 2. What is H alpha? H alpha is, by definition, 2 alpha, alpha, alpha. Alpha in the product with alpha is the length squared, so it's going to be 2, so it's just alpha. So H alpha is the same as alpha, so it's still the same with square root of 2, right? What about H beta? 2 beta, beta, beta. The length of beta is 1, so it's going to be 2 beta. So it's 2 times this. So this is H beta. The length is 2, so it is like that. So in this case, Bn check. Oh no. B2 check is the same as C2 or isomorphic, but in general or always, this is not really isomorphic to Cn for greater than n greater than 2. And you can easily see that they're, in this case, they're isomorphic, but even though they're not isomorphic, it's very easy to see that the y group must be the same, because all we are doing here is just changing one vector in one root to a constant multiple of that root. But if you have alpha and h alpha, what is S alpha? Reflection about hyperplane. Let me draw a little more carefully, just to make. So we have alpha here. So suppose that we have a hyperplane perpendicular to alpha. So what S alpha does is like S alpha kind of reflect about this hyperplane. What happens to the H alpha? H alpha is really the same with a constant multiple of alpha. So SH alpha is really the same as S alpha. So their Y group must be coincide. They have to be the same. But root system, in this case, we got the same or isomorphic root systems, but in general, our check is not isomorphic to R. Okay, I think I can stop here and see you next time.